Hey guys, welcome to chapter 14. So chapter 14 is going to be all about chemical kinetics. Chapter 14 is going to be separated into two sections. So 14A is this week, 14B is next week. So it is a pretty thick and heavy chapter, so make sure you guys are giving yourself enough time to get through it. So what is chemical kinetics? Well, chemical kinetics is where we're going to study how fast or how slow reactions take place. So kinetics is the study of how things change over time. Something we're actually really interested in as chemists, but also something we're pretty interested in is just people in general. So other examples of how things change over time would be our speed. So how many miles did we travel per given hour, right? Another thing that we like to gauge, especially here in the month of January and February, is weight. So how many pounds did I lose per month, or how many pounds did I gain per month? So there's just other examples of how we study how things change over time. For kinetics, we're going to be looking at several different types of time, and we're going to be basically looking at how concentration changes over a given amount of time. Besides information about speed, kinetics also sheds some light on reaction mechanisms. So this is something we'll get to in the B portion of this chapter, but valuable information for chemists. If we understand how a reaction takes place, so the reaction mechanism, then we know what steps there are, and more importantly, we know what steps to manipulate along the way. So reaction mechanism is an invaluable tool for chemists. It's something that's really, really important to us. So we, in other words, can get a little glimpse or a picture of how the reaction occurs. Okay. The next thing I'm about to talk about is in your textbook towards the end of the chapter. I really like to introduce it at the beginning and then kind of refer back to it all chapter. So the model that we're going to talk about for chemical reactions taking place is something called the collision model. So this is going to be the point of view that we take for this chapter. Collision model says that a reaction will occur when particles collide, and they collide with a correct amount of energy. So they need to A, collide, and then B, they need to have a certain amount of energy in order for that collision to take place. We're going to look at the details of each of these throughout the chapter, but I want to just really quickly understand what rate depends on. So if we're talking about speeding a reaction up or slowing it down, what are some things that we could do to that reaction to speed it up or to slow it down? So these are three items that rate depends on. I'm going to quickly introduce them now, and then we'll go over them in much more detail throughout the chapter. So first and foremost is concentration. So this one's pretty straightforward. Increase the concentration, you're going to increase the number of particles that are colliding, and therefore you're going to increase the rate of that reaction. So if a reaction depends on collisions, we cause more collisions to take place, then we're going to see a faster rate. Temperature. So here, if we increase the temperature of a reaction, we're going to increase the kinetic energy. So those particles are going to move faster. If we increase the kinetic energy, we got particles moving faster. That's also going to result in more collisions. So again, if we're dependent on collisions for a reaction to take place, then the number of collisions increasing is going to have that reaction take place a little bit faster. It's also going to decrease the amount of energy that we have to put in order for that reaction to take place. So part A is these particles colliding. Part B is colliding with enough energy in order for something to happen. So by increasing the temperature, increasing kinetic energy, we're also ensuring that those collisions are viable collisions. And then lastly, structure and orientation. So this one is probably new and different for you. So for structure and orientation, let's say we're looking at the following chemical reaction. And the chemical reaction is we have this AA, we react it with B, and we get this new molecule of A and a B together, okay? If we look at this compound on the bottom, now we have an AX, we react it with a B, and again, we get the same product. We get this AB complex. Well, in the first example, this B could come on this side and attack this A on the right, or it could come in from the left side and attack this A on the left. So if these two are the same atom, it can really come in from any direction and collide to get this new AB molecule. So the collision could really take place any side of this molecule. But if we look at this AX molecule, now we're limited to the number of places that B could come in. So really B could come in from the bottom, from the left, from the top, and that's it. If B comes from anywhere over here on the right, it may collide with X, but nothing's going to happen. We need A and B to collide in order to make this new molecule. So this is one of the ways that we look at structure. Sometimes chemists call it orientation. So the structure and orientation of the particles is certainly going to affect their rate. So probably a faster rate in this first reaction, slower rate in the second reaction because we've got to wait for B to find A. Okay. So 3 factors that will affect the rate. Like I said, we're going to come back to each of these at length throughout the chapter, but I think if we get an introduction to it, it's a little bit easier to frame this chapter better. So let's dive into our first look at reaction rates. So the first one we're going to look at is the average reaction rate. I'm really going to be purposeful about calling this average reaction rate because the next one we're going to look at is going to sound and feel similar, but it's going to be called rate law. So I'm really going to be mindful of calling this average reaction rate. So when you get to questions, you know what format I'm talking about. So average reaction rate is going to measure the change per unit of time. So how much did our concentration change? So let's first look at something that we're comfortable with. So if we're looking at speed, miles per hour, we're looking at the distance, so the number of miles that changed over a given amount of time. So per hour or per minute per second. Okay, so the change in distance over the change in time. Remember that this triangle is the delta symbol. That's the symbol for change, so the change in our distance. And again, we see the delta symbol, change in time. Okay, so that's something that we know, that we're familiar with. When we're looking at chemical reactions, however, we're not talking about the speed. What are we talking about? We're talking about the amount of our reactants. We're talking about the amount of our product. So the bottom is still going to be the same. We're still going to monitor this over some given amount of time. But on the top, we're going to look at change in concentration. So change in concentration. So our formula might look something like this. The average reaction rate is going to be the change in concentration of hydrogen. So I just picked hydrogen so we'd have something to look at. So the change in concentration of hydrogen over the change in time. So in chemistry, we are lazy, right? So we don't ever write anything out in words like this. We always use nice short symbols. The way that we're going to denote change in concentration is with squared off brackets. Not parentheses, lazy chemists, brackets. So these squared off brackets. So the way that I would read this is change, these squared off brackets tell me concentration, and that's of hydrogen, over the change in time. Okay. The other thing that you notice here is this little negative sign slipped in, right? So this negative sign, why did that negative sign slip in? Well, the reason that it slipped in is because we're looking at the change in a reactant. So if I have a beaker of hydrogen, a beaker of iodine, and I pour those two into a mixture together, what's the only direction that their concentration can go? Well, their concentration is going to go down, right? We're going to use up hydrogen. We're going to use up iodine, and we're going to create this new molecule, hydroiodic acid, okay? So we use these up in order to create our product. So the concentration of these guys will always go down, and the concentration of our products will always go up. So that we would see a positive if we were looking at our product. Okay. All right, so let's break this down one step further. Okay. So how do we determine the change, right? So if I'm looking at experimental data and I'm going to look at how the concentration changes over a given amount of time, remember that the change in something is always, always, always final minus initial. Final minus initial. So if I break this change in concentration over a change in time out, so if I kind of expand that a little bit, we're going to see final time minus initial time. So sometime later, sometime initially, we're going to subtract those two. And we're going to look at what was the concentration of hydrogen at that final time and what was the concentration of the hydrogen at that initial. So final minus initial, final minus initial. Okay, so that's just expanding this formula out a little bit. Okay. The last thing that we have to address before we can dive into some data, dive into some examples, is this. So yes, the reactants are always going to go down. Yes, the products are always going to go up. But what's the last thing that we need to consider? Well, we need to consider these stoichiometric coefficients, right? So the fact that we're using one molecule of hydrogen, one molecule of iodine, and we're creating two molecules of this hydroiodic acid. Okay, so we need to recognize these stoichiometric coefficients. So the way that we're going to recognize them is the following. So when we put these into our formula, we're going to put the stoichiometric coefficient as a fraction before this change in concentration over change in time. So the stoichiometric coefficient is going to be 1 over whatever the coefficient is. So for hydrogen, it would be 1 over 1. For this hydroiodic acid, this product here, it'd be 1 over 2. So we're going to put it as a fraction in front, and the number on the bottom of the fraction is the coefficient. The reason for this is we want to compare apples to apples. So we want to know what the rate is for 1 mole, 1 mole, 1 mole. So that's why it's put as a fraction. We're going to look at 1 mole of this reacts with 1 mole of this to produce 1 mole of this, and how fast does that happen? Okay, so here's that generic reaction and generic formula from your textbook. So here we see our reactant A. So we've got our change in concentration of A over our change in time. And this little a here would be the coefficient. So that could be a 2 or that could be a 3. And we see that that fraction goes in the front. Same thing with B. So change in concentration of B over change in time. That little b is the coefficient, so 1 over little b. And notice these are reactants, so they're negative. And then lastly, we have our products, same setup here. But again, just making this crystal clear that products are always going to go up. So the concentration is always going to be a positive change in the concentration. We're producing that. So let's look at an actual example. Let's throw some numbers in here and see if we can really nail this idea down in our heads. Okay. Skip over this thing. We got it. All right. So consider the balanced chemical equation. So here's our balanced chemical equation. Write the average rate of this equation with respect to iodine and with respect to H2O. Okay. So what we're going to do here is we're going to write the following. Let me get my pen here. Pen. Okay. So write the average rate of the reaction for this equation with respect to I and H2O. So we're going to say rate equals, okay? So the first I'm going to do is this iodine here. So first and foremost, it is a reactant, so the concentration is going to go down. So we'll put a negative out there. Then I see this coefficient of 3. So I need to first address that and say I don't want to look at 3 moles. I want to look at 1 mole. So I put the fraction 1 over 3. Then I'm going to look at the change in concentration of I over the change in time. Okay. And then we're going to look at H2O. So we can continue this as kind of one big long formula. So now I'm going to look at the change in water. Water is a product. So I'm going to put that positive sign there just so that I know that I thought about that. And I don't want to look at 2 moles. I want to look at 1 mole. So I'm going to put that fraction 1 over 2. And we're going to look at the change in concentration of H2O over the change in concentration, or excuse me, the change in time. Okay. So this is writing the average reaction rate for the equation. And we just happen to pick 2 of them. So with respect to iodine and with respect to water. Okay. So let's throw some numbers into this. Okay. So let's look at this. In the first 10 seconds, the concentration of that iodine dropped from 1 mole to, or molar to 0.868 molar. So calculate the average rate of this reaction. So let's go back to this. Rate equals, it's going to go down. So we're looking at iodine, right? Because that's what the concentration it gives us. So 1 over 3 times the change in concentration of iodine times the change in time. Okay? So calculate the average rate. So what we're solving for is this right here. We're solving for the word rate. So that must mean we know everything on the right-hand side of this equation. Okay? So I know there's a negative. I know there's a 1/3. Now I need to break this fraction up a little bit. So let's look at the change in time first. So this is over the first 10 seconds. So the initial time was 0, right? So before I started my stopwatch, we were at time equals 0. So the initial time is going to be 0. And the final time when I stopped my stopwatch is going to be 10. So final minus initial. 10 seconds was when I stopped my watch. 0 seconds was when I started. So final minus initial. Okay. So let's do the same thing for the top. It drops from. So the concentration of the iodine before I even hit play, before we did this reaction, the concentration was 1 molar. So that's initial, 1.0. And the final was after 10 seconds. So it was at 1 mole. We let 10 seconds go by. We dipped our measuring stick in. And at that final time, after 10 seconds, we measured 0.868. Okay. So that's how we would calculate this average reaction rate. Okay, so let's plug this into a calculator and see what we can get here. So first, I'm going to clean up that parentheses first. So 0.868 minus 1 equals. So that's going to give me a negative 0.132 divided by 10 minus 0, which is 10. Okay. Now I'm going to take negative 132 divided by 10. And then I'm going to multiply that by negative 1/3. So times 1/3 equals. And I get 0.001244. Okay. What are the units? Okay, I got a little sloppy on my units over here. So we've got molarity on top. We've got seconds on the bottom. So the units for this guy is m/s. Or sometimes what your textbook does, when you've got something on the bottom of a fraction, that's the same thing as saying whatever it is to the -1. So sometimes you will see your textbook write it like this. So molarity seconds to the -1. So these two mean the same thing, but I think this is how your textbook and how Pearson will probably show you. Okay. So what is the average rate of this reaction during the first 10 seconds? The average rate is as follows. Okay, so that's molarity per second. Okay. Another way that we can introduce this kind of data is the following. So I can give you a table, and this is a little bit more indicative of what a lab might look like. So let's say we're measuring the concentration of something. So every 10 seconds, we stick in our measuring device and we get a measurement. 10 seconds goes by, we measure. 10 seconds goes by, we measure, so on and so forth. Okay. So we can look at that average rate at any one of these snapshots, right? So what I want you guys to do is calculate the average rate of this reaction during this time interval. So between 20 and 30 seconds, what is the average rate? And we know that we're going to have to do it with respect to hydrogen because that's the only data that it gives us. So with respect to hydrogen. So go ahead and calculate that and see if you can get to the answer, and then I'll do it in just a minute. Okay. So the first thing we're going to have to do is we're going to have to write a reaction for this. Okay. So our formula is rate equals, it's a reactant, so we're going to have a negative. The coefficient is 1, so we're just going to have 1/1 times the change in concentration of hydrogen over the change in concentration of time. Okay. So expand this out a little bit. We're going to have -1/1. The change in concentration, so let's do time. The change in time is going to be 20 to 30 seconds. So final minus initial. So our final time was 30. Our initial time was 20. So final minus initial, 30 minus 20. Okay. Now we're going to look at the concentration during that time. So if we're looking at this 20 to 30 second window, that means the concentrations are these two guys right here. Okay, so again, we're going to do final minus initial. So at 30 seconds, our final time, our concentration was 0.549 molar. And initial was at the 20-second time limit. Our concentration was 0.670 molar. Okay. So plug this into our calculator. So the top here, we're going to have 0.549 minus 0.670. And again, we've got a negative number here. So negative 0.121. And then 30 minus 20 gives us 10. Okay. Again, we've got a negative inside of our parentheses and negative outside. So those two are essentially going to negate each other out or cancel each other out. So I'm going to take negative 0.121 divided by 10, and then I'm going to multiply that by negative 1, and we get 0.0121. And again, our units, we just carry them throughout the whole problem. So you can do molarity over seconds. That's perfectly acceptable. Or you can do molarity seconds to the negative 1. So that is the average rate of this reaction over the interval between 20 and 30 seconds. So that's an introduction to rate, an introduction to how we would calculate the average rate of the reaction. The next thing that we're going to do is just take this one step further and watch concentration change in a slightly different way. Hope you guys found this helpful.